Okay, so in the last lecture, we have studied partial differentiation, and then we know how to solve the problem based on the partial derivatives, and we have calculated the partial derivatives using chain rule also. Okay, so now let us take one step ahead, and then we try to have the directional derivative. Okay, so first we need to understand what is going to be the directional derivative. Okay, so I hope you are able to see the screen. Are you able to see the journal?
Yes,
Yes.
sir.
Okay.
Yes.
So now we have to think the directional derivatives. Again, so these directional derivatives are nothing but basically we are going to apply the partial derivative, but now with the direction. Okay, so up to it we have seen the derivative partial differentiation, and we have considered that when we are differentiating with respect to one variable, the other variable is treated as a constant, and so on. We have solved the problem based on this concept. Now, if we add direction to this derivatives, okay, then it becomes directional derivatives. So, how to find the directional derivatives? Okay, so when we have a quantity with the direction, okay, up to 8, whatever the functions we have considered, that were all functions without direction. Okay, and hence now whatever the functions we'll be considering will be with the direction. Okay, so basically the quantity without direction is called a scalar quantity. Okay, and the quantity with direction is called a vector quantity. So is that clear to you?
Yes, sir.
Is that okay? Are you clear about the vector quantity and about the scalar quantity?
Yes, sir.
Yes, sir.
Sir.
Okay. So what we have, if we consider the quantity without direction, because up to 8, whatever the functions we have considered, that were all without direction, and that's why they were all the scalar quantities. Okay, and now we have to go for the directional derivatives. Okay, so it is important to understand the quantity with the direction. Okay, and hence we need to understand the vectors. Okay, so first of all, we have to understand what is going to be a vector. So vector is nothing but the quantity with the direction. Now, what is the dimension of the vector? Okay, so for example, if we consider one-dimensional vector, then we write y is equal to x. If we consider two-dimensional vector, then we consider the unit vector in the two directions. In x direction, we consider the unit vector I, and in y direction, we consider the unit vector j. So when we have xi plus yj, then it is going to be the vector quantity in two dimension. And if we consider the three-dimensional vector, then we have I vector, unit vector in the direction of x-axis, j unit vector in the direction of y-axis, and k unit vector in the direction of z-axis. Okay, so if I have this direction, then how the vectors are written? So what we'll be having, suppose we have this three direction. So it is x, y, and z. Okay. So in x direction, we consider the unit vector I. In y direction, we consider the unit vector j. And in z direction, we consider the unit vector to be k. Okay, so when I write this is vector, three-dimensional vector, so we can write it as v1, v2, v3. So v1, v2, v3 are the components. okay, in the respective direction. So it is V1I plus V2J plus V3K. Okay, so these are the two ways to write any vector. So this vector, n-dimensional vector, is also called as n-tuple. N-dimensional vector is also called as n-tuple. Okay, why it is called as tuple? Because the order of this elements V1, V2, V3 is going to be fixed. So first we consider in the direction of x-axis, second we consider in the direction of y-axis, and third we consider in the direction of z-axis. Okay, so this order is fixed. Yeah, we cannot move the order, and that's why it is called n-tuple. Okay, so for this vector, we are considering three-dimensional vector space, and that's why it is going to be with the three components v1, v2, v3, and v1 is in the direction of x-axis, v2 is in the direction of y-axis, and v3 is in the direction of z-axis. So sometimes this v is also written as v bar. Okay, so bar for the vector, or sometimes direction is also written. So these are the different notation to write any vector. So this is also, when I say v is equal to v1, v2, v3, so it is a three-dimensional vector in three-dimensional vector space. Okay, with the first component in x-axis direction, the second component in the direction of y-axis, the third component in the direction of z-axis, and so on. Okay, so these are the different notations to understand the vector. Okay, so is there any doubt in vector?
No, sir.
Okay, all of you got this one?
Yes, sir, got it.
Yes,
Yes,
sir, got it.
So good. So once we are able to understand the vector, okay, now we need to understand the operator. Okay, so we have the operator. Okay, what is the operator? So this is del. Okay, this del operator is what? It is I times dabba by dabba x plus j times dabba by dabba y and plus k times dabba by dabba z. Okay, so we are familiar with the derivatives dabba by dabba x, dabba by dabba y, and dabba by dabba z. So these are the first order partial derivatives with respect to x, y, and z. Okay, so this is called del operator. Okay, this is going to be the del operator. So this del operator is going to help us to understand the directional derivatives. Okay, so there are some basic things that we need to understand. So first we need to understand the del operator because we are going to use this del operator frequently. Okay, we are going to use this del operator frequently. Moreover, when we want to have the directional derivative, okay, so there are certain things which we need to understand. So if I want to find the directional derivative, when I know there are 2 points P and Q in the vector space. Okay, so these 2 points are in the three-dimensional vector space. We'll restrict ourselves for the three-dimensional vector space. We can go for the n-dimensional vector space. Now, I want to find the derivative, the directional derivative particularly, okay, in this direction. So if I consider P, so what I'll be having, it will be P1, P2, and P3. This is the positional vector for this point P. And if I consider Q, then what I'll be having, this will be Q1, Q2, and Q3. And now we want to find the directional derivative, okay, in this direction. Okay, and we have a scalar function f. So f is a function of x, y, and z. As we are considering the three-dimensional space, so we have the 3 independent variables x, y, and z. And now I want the directional derivative of this f in this direction. Okay, so there are 3 ways to find the directional derivative. So first we have 2 points are given. Second, we are given with the vector. So A bar is a vector A1, A2, A3, and then we want to find the directional derivative of this F in the direction of this vector A bar. Okay. Now, what we can have is, suppose we want to find the directional derivative in the direction of the line given. Okay, so suppose we have the line. Now, when we say the line, it will have the direction ratios. Okay, so suppose L, M, and N be the direction ratios of line. Okay, in vector space with the dimension 3. Okay, then how to find the directional derivatives in this direction? Okay, so we have to define the directional derivative three ways. When 2 points are given, what is the definition of directional derivative? When a vector is given, how we are able to calculate the directional derivative? And when the line is given and the direction ratios of the line are given, and then how to find the directional derivative in this direction. So basically, we have to use the partial derivatives, and as I said, this Dell operator. So Dell operator is going to be I dabba by dabba x plus j dabba by dabba y plus k dabba by dabba z. So similarly, we can have del square. So del square is going to be dabba square by dabba x square plus dabba square by dabba y square plus dabba square by dabba z square. Okay, so now if we have these 2 points and then this vector and then this line with the direction ratios, and we have the Dell operator. Now, as we know the scalar function, so when we have the function of x, y, z without the directions, then it is going to be the scalar function. Moreover, if I have vector, then I need to understand how we are going to find the product of these 2 vectors, and how what are the terms associated with the vector again. Okay, so can you tell me what types of product you know for the 2 vectors?
Dot product.
Dot product and scale
Dot
product.
product,
Cross
cross
product.
product. Okay, that's good. So you are aware about the dot product and cross product of the vectors. Okay, fine. So let us try to understand what is the dot product and what is cross product. Okay, so we consider, let A bar is equal to A1I plus A2J plus A3K, or we can write this as A1, A2, A3, and B bar is equal to B1I plus B2J plus B3K, or we can write this as B1, B2, B3. Okay, B 2 vectors. Okay, when I say vector, that means definitely I'm considering non-zero vectors. Okay, so 0 vector is what? 0 bar, 0I plus 0J plus 0K. So this is going to be 0 vector. So when I consider vector, then obviously it is going to be a non-zero vector. So this this be the 2 vectors in 3-dimensional space, because we are having 3 components. So these are in 3-dimensional space. Okay, then what we know is, then we have, okay, so what is modulus of A bar? Modulus of A bar is square root of A1 square plus A2 square plus A3 square. And what we have, modulus of B bar. Okay, so this sometimes written as A, and this is sometimes written as B only. So modulus of B bar, this is going to be B1 square plus B2 square plus B3 square. Okay, so that's what we have. So first term that we know about the vector is the modulus. Okay. Now let us try to define what is the product. Okay. So we have a bar dot b bar. Okay. So what we have a bar dot b bar. So what we'll be having here a1i plus a2j plus a3k dot what will be having b1i plus b2j plus b3k. Okay, and this is equal to a bar dot b bar is equal to a1 b1 plus a2 b2 plus a3 b3. Okay, so this is why we know I dot I is equal to 1, j dot j is equal to 1, k dot k is equal to 1. And in other way, how we are able to define this a bar dot b bar is equal to mod of a bar into mod of b bar into cos of theta. Okay, where theta is angle between a bar and b bar. Is that okay? So here we are able to define the dot product of these two vectors, okay, as a bar dot b bar is equal to, if we know the component wise, okay, then we are able to calculate this way. If you know the angle between these two, then we are able to calculate this way. Is there any doubt in dot product?
No, sir.
No, sir.
Okay, all of you are able to get this one?
Yes, sir.
Yes, sir.
Yes. Okay, that's good. And also we have, okay, what we have a bar cross b bar. Okay, so this is the dot product we are able to define. What is a bar cross b bar? It is the determinant ijk a1, a2, a3, b1, b2, b3. So dot product we are able to define. The cross product we are able to define this way. Also, we are able to define this a bar cross b bar as, can any one of you tell me? Please raise your hand if you can. So can you tell me? Okay, that's great. Yeah. So this means
A B sin theta.
AB sin theta. Okay.
Hmm.
What about Prajwal?
Sir, mod A, mod B, sin theta.
Mod A, mod B, sin theta. Okay. Anshul?
So same mod A, mod B, sin theta.
Okay. So mod A, mod B, sin theta. Okay. Is there any other
And sir, direction also sin k cap.
direction also? Okay. So what is the direction? How we are able to get the direction?
Right hand thumb rule. Right hand thumb rule.
Okay. Right and thumb rule. Okay. So what we have to understand is, if I have a bar and b bar, then the direction of this a bar and b bar, okay, direction of this a bar cross b bar is perpendicular direction to the a bar and to the b bar also. Okay, so that's what we need to understand. Okay, dot product is also called as scalar product because it generates the scalar quantity after having the product. Okay, but cross product is also called as vector product because it generates the vector, okay, after its product. So here, this a bar dot b bar into cos of theta, this is all scalar. There is no direction remaining. Okay, or you can see a bar dot b bar is a1 b1 plus a2 b2 plus a3 b3. There is no direction. But if we consider about the vector product or A cross B cross. So this is going to be mod of A bar or AB, you can say directly, mod of B bar into sine theta. Okay, this is going to be sine theta into n cap, where n cap is unit vector in the direction of A bar cross B bar. Okay, and basically what you have in case of A bar cross B bar, so if we have A bar and B bar, so this is going to be A bar and B bar, then this vector A bar cross B bar is perpendicular to both. So this is A bar cross B bar. It's going to be perpendicular to both of these vectors A bar and B bar. Okay, or it is normal, we can say, to the plane in which the vectors A bar and B bar are there. Okay, so now we consider the general vector. Okay, so what is the general vector we can have? Okay, so let us consider the general vector. Okay, and hence consider R bar as a general vector. So it is xi plus yj plus zk. Okay, or this is going to be x comma y comma z. Okay, be the vector. Then what we know, what will be mod of R bar? So it is going to be R, which is going to be square root of x square plus y square plus z square. Okay, what you'll be having? X bar, R bar, mod of R bar is equal to R, which is mod of x square plus y square plus z square. Okay. Now, if we consider this is a general vector, so what you'll be having? You'll be having dr bar is equal to idx plus jdy plus kdz. Okay, so what we'll be having? Dr bar is equal to idx plus jdy plus kdz. And if you want to consider the derivative of this r with respect to x, y, and z, then we know dabba r bar. Okay, so dabba r by dabba x is equal to x by r. Dabba r by dabba y is equal to y by r, and dabba r by dabba z is equal to z by r. So this we are able to easily calculate. Okay. So is there any doubt up to 8? So is there any doubt up to 8?
No, sir.
Oh, sir.
So I hope up to this is okay.
Yes, sir.
Okay. So there is no doubt up to 8.
No.
Okay. So now if you don't have any doubt up to 8, okay. So these are the basic things that we need to understand. And now we'll define the directional derivative. Okay, so how we are able to define the directional derivative? We can say, yes,
Now, could you show that the last slide again?
1 minute, just a minute. Yes. What do we have? So here we have the vector n cap. So we write n cap or n bar. This is going
Sir,
to
you are
be
not sharing the screen.
unit vector. Oh, okay. Just wait. Okay, so now it's visible.
Yes, sir.
Okay. So this is going to be the unit vector. Okay, so this n bar is unit vector in direction of A bar cross B bar. Okay, so A bar and B bar are in one plane, and then this A bar cross B bar is in the as it is as the perpendicular, or its direction is perpendicular to the plane where A bar and B bar are. Okay, and so that's why we have to consider this direction n cap. So n cap is, or n bar is the unit vector in the direction of A bar cross B bar. Okay, so are you done with this basics?
So one
Sir, how you write debar by debar x is equals to x by r?
Pardon?
That last you wrote na debar r by debar x is equals to x by r.
This one.
Yes.
Okay. You have r is equal to square root of x square plus y square plus z square. Okay. So just differentiate this r square. What will be the term here? You'll be having r square is equal to x square plus y square plus z square. No?
Yes, yes, sir. Understood.
Yeah, you can differentiate this partially with respect to x, y, and z, and you can get this. Are you able to get it, or shall I calculate?
No, sir, I got it. Thank you, sir.
Okay, that's good. Okay, so that's why we have done the partial derivatives first. Okay, is that okay?
yes.
Yes. Okay. So if
Yes,
you
sir.
got this basics of vector and the partial derivatives already we have solved. Okay. So now we are ready to define the directional derivative. So sometimes we use the first principle of differentiation to derive, and then we use the partial derivatives also. Okay, so let us see how to define the directional derivatives. Okay, so I hope you are able to see this, right?
Yes, sir.
Okay, so the first case, when we have two points in the three-dimensional space. So we have P and we have Q. And then now we want to define the directional derivative in the direction of this PQ. Okay, so we consider first. Okay, so here we have point P and we have Q, and we want the directional derivative in this direction. Okay, so that's what we'll be having. Now, what we'll be having, let f is equal to f of x, y, z. Okay, be the scalar function and p is equal to p1, p2, p3. Q is equal to, that is going to be q1, q1, q2, q3. Okay, be the points in space. So when I say space here, that means vector space. Okay, so here we are considering three-dimensional. So easily we are able to visualize this three dimension. So that's why we are considering three dimension. Okay, then what we can have is then the directional derivative. Directional derivative of f in the direction of PQ is given as. So here, if we are considering these 2 points and we want the directional derivative, then we use the first principle to find the derivative. So how that works? So it is limit P is tending to Q. Okay, so this segment is going to be very small. Okay, so limit P tends to Q, F of P minus F of Q. Okay. So the value of this scalar function at P, and then the value of this scalar function at Q. And here we have P minus Q. Okay, so if this limit exists, okay, if it exists. Okay, so always there is a condition on the existence of the limit. Okay, so if this limit exists, then we say it is going to be the directional derivative of F in the direction of PQ. Okay, because P is going to be the vector here, Q is going to be the vector here. So this is going to be a vector function, and that's why we consider this as a directional derivative. Okay, so here, this is the first way of considering the directional derivative in the direction of P to Q. Now, the second one. So what we have, suppose we have provided a vector. Okay, so let F is equal to F of x, y, z be the function. We can say be the scalar function, and a bar is equal to a1i plus a2j plus a3k, or that is equal to a1, a2, a3. Okay, be the vector in space. Okay, then the directional derivative. Directional derivative of F in the direction of a bar is given as. So this is going to be Del F into a bar upon mod of a bar. Okay. So what we have here, this is the delta, this is del F, this is Dell operator, del F into, it's going to be a dot product. Okay, this will be a vector quantity, this is going to be a vector quantity divided by its modulus. So when we define the vector divided by its modulus, then it gives a unit vector in this direction. So where, okay, del is equal to, so what is del I have given you? I double by double x plus j double by double y plus k double by double z, and a bar upon norm of a bar is so this is unit vector in the direction of a bar. Okay, so a bar upon norm or mod of a bar is going to be the unit vector in the direction of this vector a bar. Okay, so this way we are able to define the directional derivative. Now the third case. Okay, so what we'll be having, let F is equal to F of x, y, z be the scalar function, and LMN be the direction ratios of the line in space. then the directional derivative, then the directional derivative in the direction of the line is given as. So we'll be having this is equal to L dabba by dabba x dabba f by dabba x m into dabba f by dabba y plus n into dabba f by dabba z. Okay, so these are the different ways to calculate the directional derivative. Now here we came across the term del f. Okay, so f is going to be the scalar function. This del is going to be the vector. You can see del is equal to I dabba by dabba x plus j dabba by dabba y plus k dabba by dabba z. So what this del f will be? So f is going to be scalar function. Del is going to be a vector operator. So can you tell me what this del f will be? Whether it will be a scalar or it will be a vector?
Vector.
A vector.
Yes. What it will be?
Sir,
Vector quantity.
A vector
It is
quantity.
going to be the vector. Okay, sure. So if I have this scalar and this is an operator, I'm operating this scalar on, I'm operating this vector operator on the scalar function, then I'm getting the vector function. Okay, so basically what this vector function is for. Okay, so we need to understand what this vector function is for. Okay, so we call it as gradient. Gradient of scalar function. So what we have? We have gradient of the scalar function. So here, what we'll be having, let f is equal to f of x, y, z be a scalar function. Okay. Then, put in a scalar function and L is equal to I dabba by dabba x, j dabba by dabba y plus k dabba by dabba z. Okay. Be the operator. Then the gradient of scalar function f is denoted by grad f or del f and is given as. So what you'll be having, grad f, this is equal to del f and this is equal to I dabba f by dabba x plus j dabba f by dabba y plus k dabba f by dabba z. Okay. So this is what you'll be having, the gradient of a scalar function. Now you can see here we have the gradient of the scalar function, and then already we have giving one direction to this gradient. Okay, so this gradient is already a vector function. This a bar upon mod of a bar is also a vector function, and we are having the dot product of these two functions. So you can see how we are able to define the dot product. So we know how to define a dot product of two vectors. Okay, moreover, in the next also, when we are finding the direction ratio with the help of we are finding the directional derivative with the help of the direction ratios of a line. So this is nothing but the dot product of del f and the vector, which is actually the direction ratios, the vector with the components as direction ratios. Okay, so this is also the dot product of the two vectors. One is del f and the other is LMN. This is the vector. Okay, and we are having this dot product. So this dot product defines actually the directional derivative in the direction of the line with the direction ratios L, M, and N. Okay, and then this what is del f is going to be? So del f is going to be the gradient of this scalar function. Okay, f, when we are considering f is a function of x, y, z. So it is going to be the scalar function, and we are able to find the gradient of this scalar function. Now, what happens if this Dell operator is operated on vector function? Okay, so here we have considered this as the scalar function, and we operated this operator, but we know that this operator is going to be a vector itself. Okay, so if I have to operate vector on vector now, okay, so what we have to do is, this is a vector. So we have operated this vector on the scalar, and then we got the gradient. Now, if we operate this vector on vector, then there are two ways. So either we can have a dot product or we can have a cross product. So what happens if we use the cross product? So we can have curve or rotation of vector function. So we have curve or rotation of vector function. So what we consider here, suppose f be the vector function. So now it will be f bar. Okay, so when I say it's going to be a vector function, so it is going to be f bar. So f bar I consider as f bar is equal to, with the components. Okay, what are the components here? So we'll be having f1, f2, f3. Or the other way we can write this as f1i plus f2j plus f3k. Okay, be vector function. Then the curl or rotation of f bar is denoted by del cross f bar and is given as. So what will be this del cross f bar? So it is going to be del cross f bar is equal to, so it is ijk. What do we know? Daba by daba x, daba by daba y, daba by daba z. And then what are the components of this f? So the components of f are f1, f2, and f3. Okay, so this way we are able to calculate the curve or rotation. Okay, this is also called as rotation of f bar. Now, again, what if del cross f bar is equal to 0? Okay, so that is curl of vector function f bar is equal to 0. Then the vector function f bar is called as irrotational. Is called as irrotational vector function. Okay, why it is called as irrotational? Because this is nothing but a rotation. So this is what you'll be having, rotation of f bar is equal to del cross f bar. But we know that del cross f bar is going to be 0. That means rotation is going to be 0. So if there is no rotation, then it is called as irrotational. Okay, so that's why this is called as irrotational vector field. Okay, or vector function. Now we consider the cross product. So what happens to the dot product? Okay, so if I consider the dot product of this vector field. Okay, so if I consider the dot product of this vector field, or this is also called as conservative. Okay, so we can say, or conservative vector function. Okay, so you can say irrotational or conservative. Now, we are able to define if we have the dot product, what will happen to the dot product? So it is divergence of vector function. It is divergence of vector function. So what we can have here, let f is equal to f bar is equal to f1, f2, f3 be a vector function. Then divergence of f bar is denoted as divergence of f bar or L dot f bar and defined as. So what we can have, what is the definition of this? So we can define this as divergence of f bar is equal to L dot f bar. This is W by W x plus W by W y plus W by W z. Okay, so that's how we are able to get the divergence of the given vector function or vector field. Now,
Sir, can you please scroll up a little?
yes.
Okay, sir. Thank you.
Okay, so here we have defined the curl and then we have defined the case what happens if we have del cross f bar is equal to 0. So we call this function as the irrotational vector function. What happens if divergence is going to be 0? Okay, so if we have this divergence is going to be 0. Right here, if divergence of f bar is equal to L dot f bar is equal to 0. Then f bar is called as solenoidal. And then f bar is called as solenoidal vector function. Solenoidal vector. So f bar is called as solenoidal vector function. So here basically we have seen the idea about the scalar function and the vector function. Okay, so what we have seen is what happens to the vector function when its curl is going to be 0. Okay, so if curl is going to be 0, so we call it as irrotational vector function, or we call it as conservative vector function. Okay, now if we consider the dot product and we get divergence equal to 0. Okay, then we call it as solenoidal vector function. So then we consider as solenoidal vector function. So is there any doubt?
Sir, can you please show the last slide again?
Yes, sure. Yes. Okay, so just see this. Okay. So here, when we consider the curl is going to be 0, that means it is irrotational or conservative vector function. And if we have divergence equal to 0, then we consider it as solenoidal vector function. So is that okay?
Yes, sir.
Okay, is there any doubt up to 8?
No, sir.
Sir.
No, sir.
No, sir.
So all the idea is correct up to 8?
So could you show the rotation one? I was caught.
Yeah. So all the idea is correct up to 8. All of you are able to get up to this?
Yes, sir.
Yes,
Got it.
that's good.
Yes, sir.
Sir.
So now, once we are able to understand the gradient, the curl, and the divergence, then we try to solve some problem based on this, and an idea of directional derivatives we know. Okay, so let us try. Then one thing we need to understand the maximum directional derivative. Okay, so that's also we have to understand. So here we have maximum directional derivative. Okay, so this maximum directional derivatives is in the direction of del f. Okay, so if f is equal to f of x, y, z. So when I write bar, that means it is going to be the vector function. If I do not write bar, that means it is going to be the scalar function. So we have to be careful when we want to say vector and when we want to say scalar. Okay, so f is equal to f bar be a scalar function. Then the maximum directional derivative of f is in the direction of gradient of that is. Okay, so when we consider the directional derivative, it is maximum in the direction of del f. So gradient of f. Okay, so when we say f, it is going to be scalar, f bar is going to be the vector. So now we try to solve the problems based on this. So let's go for the example based on this.
Sir, just give us a minute.
Yes.
Just give us a minute to revise.
So you can just revise this, then we'll go for examples. Okay.
Sir, it is just a simple multiplication, not a dot product of delta.
It is not a multiplication. Del is an operator. Okay.
Yes, sir.
So we have to find the partial derivatives. Okay. When we consider gradient, we don't put dot. Okay, and the next function where delta is del is operating is a scalar function. Okay, and if I have a bar, then we have to consider dot or cross, because for vectors del is already a vector. Okay, so if vector operating on scalar, it will generate a vector. and there is no other operator. If vector operating on vector, then we need to connect these two vectors either by dot or by the cross. Okay, so if we connect these two vectors del and f bar by cross, then we call it as curl or rotation of f bar. If we connect them with the help of this dot, okay, then it is going to be divergence. Okay, and then we have to consider del dot f bar is actually the divergence of f bar. So is that clear?
Yes, sir. Clear.
So,
Okay.
sir, del f is a vector.
Yes, del f is a vector. Okay. Is there any other doubt?
No, sir.
Okay. So we'll go with the example. Find the gradient of f is equal to xy square minus 5xyz plus 2z at 1 minus 1, 2. Okay, so we have to find the gradient of f, which is xy square minus 5xyz plus 2z at 1 minus 1, 2. Okay, so here we want to find the gradient. What it means, what we have to find?
LS.
Del f. Okay,
Del f.
so we have to find del f. So what will be having? Leg. Okay, so f is equal to x y square minus 5xyz plus 2z. Okay, be the scalar function, and a is equal to 1 minus 1, 2 be the point. Okay, so we have to find out the gradient at this point. Okay, what we have to do is we have to find the gradient at this point. Okay, so consider what is the Dell operator. It is I dabba by dabba x, okay, plus j dabba by dabba y plus k dabba by dabba z. Okay, so we have what we know, gradient of, this is short form I'm writing for gradient, so that's why I'm writing dot here. Okay, so gradient of f is equal to del f, and that is I dabba f by dabba x plus j dabba f by dabba y plus k dabba f by dabba z. Okay, so what we have to do is we have to find out this derivatives. So let this equation 1. So we have to differentiate f with respect to x partially, f with respect to y partially, f with respect to z partially. Okay, so consider what we'll be having dabba f by dabba x. So we have to find the derivative of this with respect to x partially. So what we get here? So this will be y square. Okay, the derivative of x is going to be 1. For this term, the derivative of x is going to be 1. We have y square. So y square remains minus. So this will be 5yz. The derivative of this x is going to be 1 again. And plus, what will be the derivative of this term with respect to x?
0.
Yes. So it is going to be 0. So then we have to find the derivative of f with respect to y. So this is the partial derivative. Now differentiate this term with respect to y. So what you'll be having here, this will be 2xy. This is going to be minus
Minus
5
5xz.
xz, and you'll be having plus 0. So dabba f by dabba z now. So the derivative with respect to z. So this is going to be 0. This is minus 5xy and you will be having plus 2. So are you able to get these derivatives?
Yes.
Yes, sir.
Yes,
Yes,
sir.
sir.
So I can write this as dabba f by dabba x is equal to y square minus 5yz. Okay, so this is going to be 5yz. Then dabba f by dabba y is equal to 2xy minus 5xz and dabba f by dabba z. So this is going to be minus 5xy plus 2. Okay, so that's what we got. Now, what I can write is from equation 1, we have, so we'll put these values in equation 1. Okay, so if we put these values in equation 1, so what we'll get is, we'll get del f equal to, so we have, this is y square minus 5yz times I, then plus 2xy minus 5xz times j, and plus this is minus 5xy plus 2 times k. Okay, so this is going to be del f. So this is going to be the gradient of f. But where we want to find this gradient, we have to find this gradient at the given point A. Okay, so we have to find the gradient at this given point A. So what will happen at this point A? So we can have at A equal to 1 minus 1, 2. Okay, so what is the meaning of this? A is equal to
X is
1
equals to
minus
1.
1, 2. So that means x is 1, y is minus 1, and z is going to be 2. Okay, so at A means what? We have to put x is equal to 1, y is equal to minus 1, and z is equal to 2 in the gradient, whatever we have calculated. So what you'll be having here, this is del f at A. Okay, so del f at A equal to, so what we have here, y is minus 1 square minus 5 times minus 1, and z is going to be 2, and this is times I, plus what do you have here, 2, x is going to be 1, y is going to be minus 1, minus 5, x is going to be 1, and z is going to be 2 times j, and plus, so this is minus 5 times x and y, and plus 2 times k. Are you getting this down? So what I am doing here, I am replacing x by 1, y by minus 1, and z by 2. Okay, and that's what we are able to get here. So what we'll be having, minus 1 square is going to be 1. This minus minus is going to be plus 10i, plus what this term is going to be, minus 2, and this term is going to be minus 10. Okay, and this is times j, plus this is going to be minus minus plus 5, and this is going to be 2 times k. So are you able to get this? So 11i minus 12j and plus 7k. Okay, so what we got here? We got this del f at A is equal to 11i minus 12j and plus 7k. Okay. So this is what we got, the gradient of f at the given point. Okay, so is there any doubt in this example?
No, sir.
No, sir.
Okay.
Yes, sir.
Okay, so you got this example.
Yes, sir.
Yeah, sir.
Yes, sir.
So let us try the another example. Okay. Find the gradient.
Sir,
Yes,
that 11 I cap will not come.
I
Or
or I cap. That is okay. So if you write I or you write I cap, J is same as J cap and K is same as K cap. Okay, so that's what I have declared, that I is the unit vector in the direction of x-axis, J is the unit vector in the direction of y-axis, and K is the unit vector in the direction of z-axis. Okay, so if you want to write cap, then that notation is also welcome. If you don't write cap, then these are directly considered, because I'm writing 11I, so it is also considered as I is going to be the unit vector in the direction of x. Okay, so that's okay. You can write it. Okay. Is that
yes,
okay?
yes, sir.
Yes. Okay. So we'll try the another example. Okay. Find the gradient of f is equal to. Okay. So it is going to be x z square. Okay. X z square minus 5 xy plus yz at 1 1 1. So we'll try to find the gradient of this function at the given point. So what we'll be having, like f is equal to xz square minus 5xy plus yz be the scalar function, and a is equal to 1 1 1 be the point. Okay, so we have what we'll be having, L is equal to del is equal to I double by double x j double by double y plus k double by double z. Okay. Then we want the gradient of this function. Okay. So consider gradient of f, that is del f is equal to. So what will be having, I double f by double x plus j double f by double y double f by double y plus k double f by double z. So consider, we can have, this is equation 1. We have double f by double x. Now calculate the derivative of this term with respect to x. So it is going to be z square minus 5y double f by double y is equal to, what is the term we'll be having here? Minus 5x plus 1 and double f by double z. So it is 2xz and
Excuse me,
plus y. Yes.
sir. Dabba f by dabba y. It should be minus 5x plus z, I think.
Yes. So this is z. Correct. Okay. So this is going to be z. Okay. So the derivative of y is going to be 1 and z remains here. So yes, it is going to be z. So now it's okay.
Yes, sir.
Yes. Okay. So what we can write is from equation 1 we get. Okay. So what we are able to get here, we'll be having Del F is equal to. So it is I. We can write this is z square minus 5y times I plus minus 5x plus z times j plus 2xz plus y, and is going to be k. Now what will be having at a is equal to 1 1 1. So here what we know, if I say a is equal to 1 1 1, so that means x is equal to 1, y is equal to 1, and z is equal to 1. So now we put x is equal to 1, y is equal to 1, and z is equal to 1. So what we are able to get, LF is equal to. Okay. So here we have, this is 1 square minus 5 times 1 I plus this is minus 5 times 1 plus 1 j plus this is 2 times x is going to be 1 now. So x is going to be 1, z is going to be 1, plus this is going to be 1, and this is going to be k. So is that okay? Are you getting this?
Yes, sir.
Yes. Okay. So now we can see this. We can calculate this terms. Okay. So let us calculate what you can have. This LF is equal to. What is the value you will be having? You can just calculate and then tell me.
minus 4i cap minus 4j cap plus 3k cap.
Minus 4
4
I cap
minus 4 j cap
minus 4 j cap
plus 3k cap.
Okay. Anything else you are getting other than this? Anybody else?
No, sir.
All of you are getting the same?
Yes, sir.
Okay.
Yes, sir.
Okay. So will you be able to solve the problem based on this concept now?
Yes,
Yes, sir.
Yes, sir.
Okay. So now we can see here, you are able to solve, or we are able to calculate the gradient of the scalar function. Okay. So easily we know how to calculate the gradient of the scalar function. What if we operate this Dell operator on the vector function? So now we'll have curl, and we'll have the divergence. Okay. So let us see the example based on the curl and the divergence. So we go with the example. Okay, so what you got here is going to be minus 4i minus 4j, and this is going to be
3K.
tk. Yes. Okay. So let's have the another example. Okay. Find the curl and divergence of f bar is equal to dx square minus yzi plus dy square minus xzj plus dz square minus xy. Okay. So this is a function given to us, and then we have to find the curl and divergence at a point we consider 1, 1, minus 1. So this is the point here. Okay, and we have to find the curl and the divergence. Okay. So we go with the solution. Okay. So what we'll be having, like f bar is equal to. So it is going to be 3x square minus yzi plus 3y square minus xzj plus 3z square minus xyk. Again, being the vector function. So now here we can identify that ijk is there, so that's why it is going to be vector. And again, to denote as a vector, I have put bar. Okay, so this is going to be the vector function, and a is equal to 1, 1, minus 1. Okay, b the point. Okay, this is the point in the vector space. Now we have to find both. We have to find out curl as well as we have to find out the divergence at this particular point. Okay, so first let us try to find the curl. So we have the Dell operator as I double by double x plus j double by double y plus k double by double z. Okay, so what is the definition of the curl? If I want to find out the curl, what we have to do is we have to consider the cross product. Yes, we have to consider the cross product. So you can see here, this f bar is going to be with the components f1, f2, f3, and then we have to consider the del cross f bar. Okay, so how do we calculate the del cross f bar? By calculating the determinant. Okay, the first row is going to be ijk, second row is going to be dabba by dabba x, dabba by dabba y, dabba by dabba z, and the third row is the component of this given vector function. Okay, so let us try to calculate this. Okay, so we have the given vector function. Okay, that's what is the given vector function. So this is going to be f1, this is going to be f2, and this is f3. Okay, so this is going to be f3. Now let us calculate the curl first. So consider del cross f bar. So what we have del cross f bar? This is ijk dabba by dabba x, dabba by dabba y, dabba by dabba z. And we have this component of f now. So it is 3x square minus yz. This is 3y square minus xz. This is 3z square minus xy. Now we know how to solve the determinant of order 3 by 3. Okay, so let us try to have, this is going to be I. Okay. Now when I consider I have to consider the product of these two and the product of these two. But here, these are the derivatives. Okay, so we have to be careful. We cannot say just only the product. So these are the derivatives which will operate on these terms. Okay, So what I'll be having dabba by dabba y of ez square minus xy minus dabba by dabba z of y square minus xz. Okay, minus j. Okay, then we'll be having dabba by dabba x of z square minus xy minus dabba by dabba z of x square minus yz, and then plus k dabba by dabba x of 3y square minus xz minus dabba by dabba y of x square and minus yz. Okay, so are you getting this determinant?
Yes, sir.
Okay, so let us simplify. What you will be having I, the derivative of this term with respect to y, so it is going to be minus x minus the derivative of this term with respect to z, so it is minus x minus j. The derivative of this term with respect to x, so it is going to be minus y minus the derivative of this term with respect to z, so it is minus y plus k. The derivative of this term with respect to x, so it is minus z minus the derivative of this term with respect to y, so it is minus z. Okay, so you can have, what is the derivative? What do you got the bracket? So it is going to be minus x plus x 0. Okay, then what you got here? Minus j into 0 and plus k into 0. So it is going to be 0. So what we got here? We got
Irrotational vector space.
L cross F bar is equal to 0. So what we got here? Del cross F bar is equal to 0. So what we can say is, that is, okay, this is the additional information that we can say. F bar is irrotational. Okay, this F bar is going to be irrotational vector field, or it is called also irrotational force field. So if we consider F bar is going to be the force in this given direction, okay, then it will not work, or it is irrotational. There will be no torque generated because of this force. Okay, there will be no torque generated because of this force. So that's why we call this as irrotational force field. Okay. Now we calculated the curl. Next is we have to calculate the divergence. So there are no term. That's why at A we are not able to get anything. At A again we'll get 0 because there is no x, y, and z that you can replace. Okay, so it is clearly 0. So that is going to we don't have any term x, y, z here to replace. So at A it will be 0 only. Or we can write here, hence at A also it is going to be 0. So we can write here, hence L cross F bar, okay, at A is also 0. Okay, because the question was like that, to find the curl and divergence at this A. So again, at A it is going to be 0. Okay, now.
Sir,
we,
could you scroll up for a second?
Yes, yeah. Sufficient?
No, sir, a bit above the matrix.
Matrix is not determinant.
Determinant, sorry, sir.
Yes.
Thank you, sir.
Yes. Okay, are you done? So let us go for the divergence. Now we have divergence of F bar is equal to, here we have, this is del dot F bar. So it is dabba by dabba x of dx square minus yz plus dabba by dabba y of 3y square minus xz plus dabba by dabba z of 3z square minus x square. Okay, so that's what we'll be having here. So it is dabba f1 by dabba x, dabba f2 by dabba y, dabba f3 by dabba z. Okay, so that's what we have here. This is equal to, what is the derivative of this term with respect to x? We are finding the derivative with respect to x. So is it 6x? Is it 6x?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, is this 6y?
Yes, sir.
Yes,
Yes, sir.
Is the last term 6z?
6Z.
Okay, so this is going to be 6 we can have common. It is going to be x plus y plus z. So what we get here, del dot f bar is equal to 6 times x plus y plus z. Okay, so here we have the values x, y, and z, and so we can replace these values. So we can write here. So at A, what is the point A? 1, 1, and this is going to be, what is the given point? Minus 1.
1, 1 minus 1.
So 1, 1 minus 1. So this is the point 1, 1 minus 1. Okay, we have del dot f bar at A is equal to 6, 1 plus 1 minus 1. So it's going to be 6. We got here del dot f bar, okay, at A is equal to 6. So please be careful while writing for this divergence. Do not forget to write dot. Okay, because if you not write dot, then it will be a meaningless expression because del cannot operate on f bar. Okay, so either del will operate on f if there is no dot. Otherwise, there should be either dot or cross. Okay, so is there any doubt here?
No doubt, sir.
Okay, so all of you got this idea of calculating the curl and the divergence.
yes, sir.
Yes, sir.
Okay, so here we were having that curl is equal to 0. So we can say that the force field given to us is going to be the irrotational or it is conservative force field. But we calculated the divergence and we got the divergence to be non-zero. So we cannot say that the force field is solenoidal at the same time. Okay, this is also possible that the force field is going to be conservative and solenoidal at the same time. Okay, but here this force field is not going to be solenoidal, but it is going to be conservative. So it shows that the curl is going to be 0, but the divergence is not going to be 0 for this example. Okay, so is that okay? Is there any doubt? Is there any doubt? All of you got this example? Have you got this example? Or have you got these concepts?
Yes, sir. Got it.
Okay.
Understood.
Yes, that's good.